So the purpose of my talk today is to tell you about the developments in quantum algorithms in the last 5 to 7 years that I find most exciting. And I decided to focus on what I consider the most interesting developments in the world. So none of them actually come from the group that I'm leading, but these are the things that I find the most interesting. And I will start with a general point. We often hear about quantum software stack, and there are these pictures that have quantum algorithms on application on one end, quantum chips on the other end, and then there's a lot of middleware layers. But really, in this picture, there are some layers that are much more difficult than others. And in my opinion, the three most important layers are first, quantum chips themselves. If we don't have a quantum chip, our field is meaningless. Second, quantum algorithms. Quantum algorithms provide applications for quantum computers. They are what makes quantum computers useful. The difference between quantum computer being extremely useful and quantum computer being very expensive but useless is having algorithms for the right problems. And the third layer that is extremely important is quantum error correction, because as we all know, quantum computers are noisy, and it's probably hopeless to hope that the level of noise in quantum devices can be reduced to such small numbers that we see in classical computing. So on quantum error correction, when Richard Hamming invented classical error correcting codes in late 1940s, the vision that he had was actually fault-tolerant computing. What he was dreaming was classical data encoded into Hamming code and computation carried out without decoding it to protect against errors. And it turned out that classical computing elements could be turned reliable enough, that so reliable that there was no need for this vision of Richard Hamming from 1949. No one does fault-tolerant computation on a classical computer because it's not needed, but it will be needed quantumly. So one general thing that I find very interesting, which has emerged in the last 7 years, is the use of block encodings and quantum singular value transformation as an all-encompassing framework for quantum computing. So there was this paper called Grand Unification of Quantum Algorithms by Isaac Chung and collaborators about 5 years ago, which shows that a lot of different things from quantum search to Hamiltonian simulation are actually instantiations of one very general framework. And what this framework is based is the notion of block encodings. So the idea of block encodings is that we have some matrix describing our problem in whatever way, and we design a unitary transformation that encodes this matrix as a part of it. So matrix that we have is that describes our problem is not necessarily unitary, but we find a unitary matrix that has our matrix as a part of it. Or more generally, it might have our matrix times some scalar as a part of it. And block encodings could be exact or approximate. Exact means that this block is exactly equal to our matrix. Approximate means that they are approximately equal in some matrix. And here is an example how one could use block encodings. So this is basically quantum linear algebra or Harrow-Hasidim-Lloyd algorithm for solving linear equations on a quantum computer done through block encodings. So the task is to solve a system of linear equations. We can write system as AX times B. A is the matrix of coefficients, X is the vector of unknowns, and when you multiply A by X, it should be equal to some known vector. So the idea of the HHL algorithm, which made a lot of noise 15 years ago, is that you design a quantum state that describes the numbers on the right-hand side of the equation. So you know these numbers. So you could hopefully make a quantum state with them as a coefficient. And then you are trying to apply inverse of the coefficient matrix to get a quantum state in which the amplitudes are the unknowns that you want to find. And here's how one could do it with block encodings. One first designs a block encoding for the coefficient matrix. Then there is a way how to transform a block encoding for a matrix A into a block encoding for A inverse by applying the respective unitary that block encodes A several times. And then we get a block unitary that has A inverse as one block. And then we apply it to the state B, in which amplitudes are the numbers on the right-hand side of the equation. And then if we have part of this unitary is A inverse. So what part of the quantum state that we get is the state that contains solution to the system of equations. So what this gives is a superposition of two quantum states. One is a solution, the other is some garbage. So at the end, one measures whether one has a solution state or garbage state. They are perfectly distinguishable. And if we are lucky, we have the solution state. And more generally, this is an instance of a general thing called quantum singular value transformation. So let's say that we have this unitary that has our interesting matrix A as one block. We can okay, I think I corrected this a bit wrong. Okay, in the next lines, most of use should be A's. Okay, so this interesting matrix A, we can describe it by its singular values and singular vectors. And then we can think of a matrix FA, which has the same singular vectors with function f applied to singular values. And let's say that f is a polynomial of degree k. In that case, we can turn a block encoding of A into a block encoding of f of A by using the unitary that block encodes A k times, where the k is the degree of a function. So we can go from block encodings of a matrix to block encodings of functions of this matrix, if these functions are either polynomials of small degree or they are well approximated by small degree polynomial. And this is how one could go from block encoding of A to block encoding of A inverse, which I described on the previous slide. One takes a low degree approximation of A inverse and applies this singular value transformation framework. And it turns out that it describes, in this framework, one can describe most of the major quantum algorithms that one have. Search or amplitude amplification fall into this framework. One just applies a polynomial to an amplitude which amplifies this amplitude. One can describe quantum counting and phase estimation. That also falls within this framework. One can apply, well, as I described, one can describe quantum linear systems algorithm by HHL. And one can also describe the Hamiltonian simulation in this framework. So this pretty much encompasses all the most well-known quantum algorithms. Okay, now let me switch to another general point. As quantum computers are becoming more and more powerful, there is more and more interest in finding out what would be the first algorithms to run on quantum computing. And there is this very detailed, more than 100-page study called Quantum Algorithms, a survey of end-to-end complexity, in which they take all the main quantum algorithms and for which each of them work out what are the obstacles towards using it on a quantum computer and how much resources would we need to do something useful. So this study appeared as a preprint a couple of years ago, and it's coming out as a book by Cambridge University Press in a few months. And one major point that they make, and it's also a point that I have observed myself many times, is that quadratic and subquadratic quantum speedups are actually extremely common. On the other hand, if we have a quadratic speedup like Grover's search, it's not clear at all if this speedup will survive all the overheads involved in building a quantum computer. So a quantum computer is going to be more expensive than a classical computer. It's going to involve a lot of quantum error correction. It's going to involve a lot of other overheads. If we get just a quadratic speedup, it's not clear if it will be worth it. On the other hand, if we have exponential speedups, then the difference between classical time and quantum time is so huge that there is no doubt about usefulness, as we can see from quantum supremacy experiments. The first Google quantum supremacy experiment was eventually simulated classically, but then they just threw in a few more quantum bits and it became impossible to simulate it again. Exponential running times go so fast that even if you can simulate them classically at 50 qubits, 70 qubits will still be well beyond anyone's reach. And actually, if one had a polynomial speedup that was larger than quadratic, it might be useful. And in this survey, they make a point that say, if one say developed a quantum algorithm with, say, 4th power speedup over classical, it might still be useful. Or at least it would have much better chance of being useful than quadratic speedups. And over the last few years, there have been a few ideas how one could go beyond quadratic speedups in new ways. And I'll quickly talk about 2 of them today. Okay, so one is this complicated sounding thing which is called decoded quantum interferometry. When I first heard this term, it really scared me from reading this paper. I think now I understand what it actually is. So it's a method for solving constraint optimization problems. So in a constraint satisfaction problems, we have some variables and we have some constraints that they have to satisfy. These constraints can be logical operations like ANDs. These can be linear equations on a small number of variables. The basic idea of constraint optimization problem is that you have a large number of variables. You have constraints with each constraint involving, say, 2, 3, or 4 variables. And ideally, you would like all of these constraints to be true at the same time. If you can't do that, you at least want to make as many constraints as possible to. And constraint optimization problems are very common in optimization. And other fields, there's a lot of things that one can turn into constraint optimization problem. I once had a student who was doing some work in natural language processing at the same time. And in natural language processing, a lot of the way how they were solving a lot of things was by reducing them to constraint satisfaction and then throwing them into some standard package for solving constraint satisfaction problem. And this decoded quantum interferometry, what it does is it achieves a provable quantum advantage for one specialized constraint optimization problem called optimal polynomial intersection. Okay, so this is another scary sounding thing. A way how one can think of this problem is as a problem of decoding and error correcting code under some set of constraints on the noise. So it's basically an error correction cryptography problem. And the algorithm is actually quite general. It's applicable not only to this problem, it's applicable to a lot of constraint satisfaction problem, but this problem is where they can show that this algorithm works efficiently in polynomial time under certain scenario, and for a scenario for which classical algorithms are not known to work efficiently. Okay, and here is one slide with a key technical idea of decoded quantum interferometry that I was able to extract out of this. So it relies on quantum Fourier transform. Now, quantum Fourier transform is something that has been useful for a lot of quantum algorithms. Factoring is based on quantum Fourier transform. A lot of other things is based on quantum Fourier transform, but they do something new with the quantum Fourier transform. So what they do is they turn this problem of optimization or constraint satisfaction into a problem of decoding a code. So they apply quantum Fourier transform, and then this constraint satisfaction problem turns into a coding problem. And yeah, in a little bit more detail, what they want is they want to generate a quantum state in which the combination, which consists of all possible combinations of values for variables, and in which the combinations that have most constraints true have higher weights than the others. So they want to generate a quantum state that is quite heavily concentrated on the best choices of values for the variables. And mathematically, the state of this type that they found easiest to generate is the one in which coefficients are polynomials in terms of the number of constraints that are true for the particular choice of variables. And then they have this state, and they consider Fourier transform of this state. And this Fourier transform has quite regular and predictable form. And if one can decode a certain error correcting code, one can generate Fourier transform of this state, which we can then Fourier transform into the state itself. And then out of this state, we likely get values of variables that satisfy a lot of constraints. And what is interesting to me is that the building blocks here are essentially something that we have known for a while. Quantum Fourier transform is what we know, what we have known. Doing an error correcting code is something that we know too, and if we have to encode, if we have to decode a quantum error a classical error correcting code by a quantum circuit, that would probably be an easy exercise into quantum coding. But these components are put together in an unexpected way, and this brings to unexpected results. Okay, now here is the second example. This is also about constraint satisfaction problems. There was this paper, Mind the Gap, achieving supergrower quantum speedups by jumping to the end. The character on the left is what you find if you Google supergrower. Then you have the first thing that comes up is not the paper, but this cartoon character called supergrower. So yeah, so this is something that was inspired by a adiabatic quantum algorithm. In the adiabatic algorithm, we encode our problem into a Hamiltonian that has solution to the constraint satisfaction problem as the lowest energy state. And then we slowly change our Hamiltonian to this Hamiltonian, and this hopefully brings our quantum state to this state. And the keyword for adiabatic algorithms is slowly, and most of the time it has to mean exponentially slowly. So this short pass algorithm is a new twist on this. The new twist is that we don't change Hamiltonian slowly. Instead, we change it into two jumps. So what happens is that success probability goes down a lot. Adiabatic algorithm is a very slow algorithm that gives you quite exact results. Here, what you have is a very fast algorithm consisting of two jumps of Hamiltonian making two jumps, which succeeds with a tiny probability. The key is that although this probability is tiny, it looks like it's still more than what one can achieve classically. So this probability is exponentially small, but it's a better exponent than what you can achieve classically. And then you can repeat this algorithm, or you can quantumly amplify it via grower, whatever you prefer, and whatever the coherence times of your quantum computer allow. And yeah, and in this paper, they found this, again, this specialized constraint satisfaction problem called K-spin problem, which classically requires 2 to the n time. And they were able to show that quantumly you could do a speed up that is just slightly above quadratic. So it's like power 2 to, it's 2 to power 0.499999. And this is what they could prove. In computer simulations, they actually got a somewhat bigger superquadratic quantum speedup. And yeah, so what's common to these algorithms is both of these algorithms achieve more than a quadratic advantage over the best classical algorithm that we know. They do it for pretty specialized problems, but the algorithms itself are fairly general. There is no obstacles towards applying these algorithms to any constraint satisfaction problem. The main obstacle is under which scenarios can be analyzed them and prove results about them. And they are both based on an interesting new ideas. And hopefully this is the beginning of a road towards better quantum solution for constraint satisfaction problems that would cover much wider range of problems. Okay, now a few more points very briefly. Another hot field is quantum machine learning, which is attracting a lot of contradictory opinions. So there is a lot of excitement. There is this recent EU position paper on quantum and AI, which will likely become a basis for a European program in this field, which says that in its introduction, but early evidence of quantum advantage illustrates how uniting AI and quantum resources could bring value. And at the same time, there are scientists who are substantially more skeptical. It's enough to go to Wikipedia article on quantum machine learning, and you can find some juicy quotes like this one. I have not seen a single evidence that there exists a meaningful machine learning task for which it would make sense to use a quantum computer and not a classical computer. Ryan Zwecky from a well-known research group at Free University. Yeah, so where is the truth? The truth is what we don't know. And this, in my opinion, this underlines the importance of provable results about quantum algorithms in general and quantum algorithms in machine learning in particular. Because as long as what we have are noisy simulations on 30 qubits, one can claim things one way or the other way. It's only the provable results that demonstrate the quantum advantage at this point. And they are difficult. They are particularly difficult for machine learning because then one also has to manage to model practically useful tasks, which is non-trivial. And lastly, a very general point is that we are somewhere in the middle of the road to practical quantum computers. We can perform quantum computations that consist of a few hundred or maybe 1,000 of quantum gates, depending on what type of quantum computers one take. Ion traps have lower error rates, so one could perform longer computations there, even though the number of qubits is still a bit less. And if you look at these end-to-end calculations where quantum advantage kicks in, for chemical simulations, one would need about 1 million quantum gates. So what we have done is, so where we are is a halfway of a very long road towards quantum advantage. So beginning of this road would be 1 quantum gate. We are at 1,000, we have gone 3 orders of magnitude. We still have 3 orders of magnitude more to go. And the rest of this road, in my opinion, is a task for both physicists and computer scientists. There is a hardware task of building a better qubits, and there's also a software task of building algorithms that need less resources, which is an enormously challenging software task, on which we are making progress, but only in slow increments. And this is why we need quantum algorithm designers. So quantum algorithms matter a lot. Thanks.
Maybe one question from audience here.
You mentioned regarding the overhead and which comes at the cost of error correction or error mitigation. Do you think that some provable results would also be available in the context of hybrid quantum computing? Because so the idea is that we would still use a lot of the classical resources and then use that essentially to extract the data from the results of the quantum results. So what is your on that?
I think that's one of the most important scientific questions in this field, provable results on hybrid computing, and I think we will eventually get there. I'm trying to work on it, but it's difficult.
Thank you.
Thanks again, Andres.